First of all, we start from the simple model, like one transmitter, one receiver, okay? And we look at the inside the transmitter and receiver, and we can model each one like this using the block diagram. And inside the transmitter, as you see here, we have a power control block. We also have a modulation encoding, okay? In the channel, we have a fading multiplied with the channel and also the noise, which is added. And the receiver, we do the demodulation and decoding, also the channel estimation. There are three different ways of running this system, right? The first one is a variable power allocation, which means that you have a power control block which controls the power, transmit power, so that sometimes you allocate the high power, sometimes low power, depending on the channel. So therefore, this transmitter has to know the channel. Therefore, the receiver has to feed it back to the channel, back to the transmitter, right? So that's you have a feedback channel which delivers the H hat, the estimation of the channel, right? That's what that's estimated here in the channel estimation block in the receiver, okay? And using this information, and in this case, actually, this is wrong, right? This information can only go to the power control block, because this one we are not changing in this block, okay? So you can fix this modulation coding no matter what the channel is, and using this channel, estimated channel, you can control the power. And this is an example, right? This is the variation of the channel over time, and when the channel has a deep fading, you allocate the high power so that these two can cancel out, so that some low channel, high power, so these two will be somehow cancel out. Therefore, you have a constant SNR. Okay, so that's the goal. Make a constant SNR. You make this power allocation to be inverse of the channel. Okay, so that is the goal. So somehow, generally, when you have a constant power transmission, you have a low performance, right? You have a high bit error rate here because you have a bad channel. And relatively here, when the channel condition is good, you have a low bit error rate, right? Your bit error rate, instantaneous bit error rate basically changes depending on the channel, right? But using this variable power, you can make a constant SNR, therefore constant bit error rate. Another way is that maybe we can fix the power, okay? Make a constant power, but we want to change the modulation coding depending on the channel. Again, since you are adapt your modulation coding depending on the channel, you again have to feed back the channel estimation. Okay, and then here's an example. This is again the channel variation. When the channel condition is good, for those time you use some higher modulation. When the channel condition is bad, then you can use another modulation, which is typically lower. Okay, that way you can actually change the number of bits to transmit. Maybe 1 bit, 2 bit, 4 bit, something like this, right? That's why we call it as a variable rate, because you change different number of bits depending on the condition. You can do both. Maybe it's better, right? You can change the power. At the same time, you can also change the modulation encoding. Okay, you can do that. But when you run this kind of system, we have to somehow think about how to change it. Okay? The first system, where you have only power control, then as we have seen already, the strategy is that we want to make the power allocation to be inverse of your channel variation. Okay? That's a strategy. Second thing here is that strategy here is that you have to find out this threshold. Okay? You have to find out this threshold, and also you have to decide how many modulations, how many steps you want to have. That's your that one you have to decide it. But once you decide it, right, then then it's pretty good. But here, in this case, now we are changing both of them. So how do you change the power control power, and how do you decide the number of steps and modulation? That's the question. So what I'm saying is that when you formulate the problem, in this case there are two variables. You may want to change the power, you may also change the modulation coding. So putting these two variables together into your problem, right? Somehow you have to formulate like a second order optimization problem, something like that, right? It's a little bit more difficult to decide how to now change the power based on what, and how to change the modulation coding. So this is a little bit difficult problem. You understand what I'm saying? Okay. So in order to make this system to be optimal, this is not a simple problem. And not only that, what is the main problem about this one? As I said earlier, for power control system, right? Yeah. Power control system, it has some problem. The problem is that always the feedback is outdated somehow, right? Because of this H is measured, is estimated here, and by the time you send it back to the transmitter using feedback channel, this H may have been already changed. Okay? So therefore, this power control may not be working as you expected. So therefore, typically a lot of people are not trying to do the power control like this way. You probably see the power control in many different contexts for many other purposes. But this purpose, I'm talking about this one, right? This purpose, variable power allocation, what they are trying to do is a power allocation based on the time variation of the H, right? But time basically changes because of this delay. Therefore, this system is not that popular. So therefore, of course, this is also not that popular. But what is popular in actual system is this one, variable rate. But here, you probably have the same concern. What is the concern? This H hat may not be exact, may be outdated. Let's say then this H hat is outdated, then what happens? Okay, let's say you measured H at this point. So now, based on the estimated H, you decide that, oh, I have to use a modulation too. And by the time you send the feedback, time has changed, so maybe you have gone here. Okay? Still okay. But now, let's say you estimate here, and by the time you send the feedback, maybe the channel condition has gone to here. Okay? In that case, you are supposed to use this one, because now the new channel condition is here, but you already measured here, right? So you use this modulation. In that case, you have a little bit higher bit error rate than you hoped. That's the loss, okay? So what it means is this system, again, because of this delay, may not be perfect, but at least better than doing nothing. I mean, there may be some delay, but typically when you do the analysis, when you design the system, this delay is kind of ignored. And there are also other techniques that you want to make the system to be insensitive to the delay. Okay, but anyway, this power control is pretty sensitive to delay, but this one is less. So this is popular. This is the example. This one basically shows you adaptive modulation table. And this table you see a lot of all these threshold value. Each one has the unit of dB. Okay? And this is the modulation order. This is QPSK, 4 QAM, 16 QAM, and so on. And how to get these values are actually this threshold. Okay, this threshold. So how to get this threshold is that you plot the bit error rate, or actually symbol error rate, you plot the symbol error rate for all these possible modulations. If you're interested, say BPSK, QPSK all the way to 64 QAM, then you plot the symbol error rate for all these modulations. Okay? And then you also have to think about what would be my target bit error rate. In this case, I set it to target bit error rate is 10 to the minus 2, which basically means that whatever happens, I always want to meet this bit error rate. Okay? Whatever it happens, I want to have my system to have lower than this bit error rate. Okay? This is the maximum bit error rate that I can allow. Okay? So that's what it is. So as long as my bit error rate is lower than this, I'm good. So in the low SNR, when SNR is very low, you start from bit error, the BPSK. Okay? And as the SNR goes higher, like this, you follow this BPSK. And then at this point, when the SNR is somewhere here, now you know that QPSK at this point have the bit error, the symbol error rate of 10 to the minus 2. So now you switch it, because even switch it, the QPSK can give you the 10 to the minus 2, right? So you switch it. Instead of just keep going down, you can switch the 10 to the minus 2 so that instead of 1 bit, you can transmit 2 bits, and also you satisfy the target bit error rate, right? So you switch it. And keep going down, and again you switch it. Now you can transmit 3 bits, 4 bits, right? So that's how you decide this threshold. Okay? So from there, now you know that the SNR range of between here and here, we want to use a BPSK. Between these region of SNR, we want to use QPSK, and so on. Okay? Yeah. Remember that this region, this first region, it's up to you, right? This region, your target bit error rate will be violated anyway. Okay? There's no modulation less than BPSK, right? So therefore, you can either transmit nothing because of your VR is violated, or you have to just transmit and this is violated anyway, so you can just go with it. Either way. Okay?
Cost is again your power. Like when we were discussing the last basic power control, we said that it's not as sensitive, or it is more sensitive than the other one, the adaptation, modulation adaptation.
Okay.
If we are talking about this one, and we are taking the false decisions, so the cost is again either it's a bit error rate, and in the reverse case we are spending more power. For example, if we were to transmit bit error rate in BPSK, and we are transmitting in COM, we are transmitting more power. So the cost is again the power. Is it the is there a correlation, or because then how you compare both systems, power control and this one?
Okay, so you're talking about this system or this one?
The power control.
Yeah.
First one,
The first one. The first one here, basically the assumption is that we are not changing the modulation coding. So from the bit error rate perspective, what you're saying is right? You can actually, in this case, we are not changing the modulation. So therefore, you just follow one curve. Just keep going down. Okay, if you use a power control like this, right? Then this is the bit error rate. For example, for QPSK, suppose that you use QPSK. Okay, then you use QPSK forever. Then here is the symbol error rate for QPSK, right? Doing the power control, basically you change the operation point from here to here, right? Basically, if you don't do the power control, then maybe when the SNR is low, your operation point is somewhere here with low SNR region. But since you allocate the high power, your operating point now is changed to here, right?
So the cost is power.
Yeah, in that case, cost is power. Not necessarily, because here, when you say cost, right? What that means is that will be some expense. Okay, that's a cost, right? But in this case, I probably don't think this is a cost because think about the average power. You allocate the power like this, right? But we want to make sure that the average power is maintained. So what that means is here in this case, average power is somewhere here. What that means is when the channel condition is good, you basically steal some of the power from here and allocate to another time instant. So you are doing uneven time allocation. That way the average power is still maintained. So this is not an additional power that you have to have. If this is additional power, that would be the cost. In that sense, yeah, your saying is right. But if that's a strategy, okay? That up to you how to run it. But typically the average power is still maintained, but I take some of the power from here and put it here. In that case, the average power is still okay, so it may not be a cost. In the other case, this case, right, we are not trying to make the same constant BER. What that means is we are taking advantage of variation of the time, okay? And sometimes we want to use higher modulation so that we can transmit more bits. So in that case, our goal is transmit more bits, variable rate, right? We are transmitting more bits so that we can increase the rate. Whereas in the previous case, we want to keep the low bit error rate. So bit error rate is our metric in the previous variable power system. In this case, probably bit error rate is not our goal in this case, right? In adaptive modulation, as long as my target bit error rate is satisfied, then I'm okay.
In fact, I have the concern when I was comparing both systems.
Mm-hmm.
Because when discussing the curve, it shows that, for example, if the condition is like not good or good, and you are transmitting in BPSK, and you are still, due to the false decision, you are still transmitting in QPSK. It means
false. False what?
No, without having the exact estimation of the channel.
Okay.
Talking about that case.
Okay.
And then again, the cost is power. So I was confused in comparing both systems. Like how, as you said, that power control is not as good as the other one is. So that's what I was confused about.
You're talking about sensitivity, huh?
Yeah, but
Yeah,
the
somehow.
average power concept is.
Yeah. But the thing is that, think about it this way. So channel is changing every time. If the channel, we typically assume a quasi-static channel, which means that our channel is like a staircase function. Okay, that's what we say as a quasi-static. During a certain duration, we just assume that the channel is constant. And on the next instant, next symbol transmission, we make another constant, but that value and the previous value can be different. Okay, so like a square case. But actual channel is not like that, right? Actual channel is constantly changing. So assuming that case, let's say our delay of the feedback is this feedback. Okay, this feedback always has a delay. Let's say this delay is very tiny, like only this much, like this much. Okay. In that case, think about the power control system like this. This is constantly changing. So even with a very, very tiny delay, still you have a different value, right? So it's always, you think that this is always wrong. Maybe it's a little bit wrong. Maybe if this is go like a very steep curve, maybe it's completely wrong. But still, it's wrong. You may not be. You cannot have the exact value. However, in here, since we are taking a discrete value, we are not taking continuous one, right? The power control is continuous variable. In this case, it's discrete variable. So let's say we have a tiny delay, same delay. If you have a delay here, it's okay because all these values are still belong to this one because we have discrete. So that's what I'm saying. If you're unlucky, then you are here, and because of the delay, channel goes down here, right here, only in here. In this case, you are maybe in a little bit bad situation, but that's the only case. Okay? That way, the power control is more sensitive. Okay. So anyway, that's how you run the adaptive modulation, and that's how we determine the thresholds. Okay. And by the way, this is the case of no coding. Okay, we talked about modulation and coding, but in this case, we assume no coding, just the modulation. Okay, now then, let's think about only coding, no modulation. Okay, no modulation means that modulation is BPSK. We are not changing modulation. We just fix the modulation and let's change the coding. As I said earlier, there are many different codings, many different codings. But these are some of the examples that are provided in MATLAB. That's why just to show you an idea, just to choose these different codings. And you know that each different coding has a different gain. But in actual system, as I said earlier, you are not doing this. Because if you want to use these many different codings, you have to have a hardware, you have to have a decoding, encoder, decoder for each of them, which is unnecessary. That's why what typically actual system does is that they fix the coding type, like a convolutional coding or turbo coding. And inside the convolutional coding, there are some parameters, okay? Like a convolutional coding, this is one example. Maybe you use hard information or soft decision. But what is more important is that when you implement the convolutional coding, there is a depth of the convolutional coding because convolutional coding is based on the iteration. So once you make a longer depth, that basically gives you better performance, okay? Which takes a little bit more delay, more processing, computation processing, process complexity, but still the convolutional coding, inside the convolutional coding, you have a parameter which you change it to get another performance, okay? So that's how you play. So you use only convolutional coding, and by changing the parameter into different values, you can make different curves, okay? So that's how actual system does, right? So now what really actual system does is that they pull this together. Like you make a combination. For example, BPSK with the convolutional coding with the coding rate 1/3. Okay? And another case is like a QPSK with the convolutional coding, a coding rate with 2/3. Things like that. You change the coding rate. You also change the modulation, right? So you make a combination. Okay, with this modulation, with this coding rate, that modulation with that coding rate. So you can make so many combinations like that. And then once you do that, now what you do is that you run the simulation like this. Okay, not exactly like this, but looks similar. Okay, so you say you use a module BPSK with the some coding rate, then maybe you have this curve. You make another combination like a BPSK with some other coding rate, then you may have another curve like this. And using the QPSK with some code rate, maybe you have something like this. So you make like tens of graph because you can have so many combinations, right? Let's say you have 3 modulations and 5 different coding rate, then you can have 15 different possible combination, right? You draw all this. You plot the symbol error rate for all these 15 combinations. Okay, that's how they do it. But that can only be done in simulation, because typically the convolutional coding, turbo coding, those coding is very hard to be analyzed. This one, right? The bit error rate, symbol error rate. We can draw this one with the analysis. We know that this one is same as Q function. All the other one also can be approximated by Q function. We know that, right? In mathematics, we can model each of these bit error rate, symbol error rate curve using Q function. So we can draw this one easily in MATLAB, just one line. Okay, MATLAB will give you this one. However, the convolutional coding, turbo coding, it's typically very difficult to find out the equation. So we only have to do simulation. So putting those things in simulation, then you have a 15 different curve. And once you do that, then what you can notice is that all the 15 different similarity curves are not equally distanced. Some of the combinations, for example, BPSK with some rate, coding rate, QPSK with some lower with a code rate, maybe almost overlap. Okay, something like that. So from those study, let's say you plot the whole similarity rate of all 15 of them, then now you have to decide which one you want to use, which one you want to drop. Okay? Because these 15 combinations are not evenly spaced, you have to decide, and you have to select only some number of them, only some distinguishable curves. Okay? And those combinations are what you are going to actually use. Okay? That's what people do when you go to the standard meeting, right? And when you go to some company who are doing some research like this, right? That's what they're doing. It takes a lot of time because all have to do simulation and have to think about what the modulation is good, what code rate is what we need to have, make a combination, right? And it takes time, but people do that. And finally, they bring out this kind of table, okay? Which is actually LTE case. Modulation QPSK with some code rate, then you combine these two, then you achieve the spectral efficiency of this one, right? Then using the same QPSK, the LTE does not use BPSK. Okay, they only have QPSK. They consider 3 different modulations. And in this case, they use QPSK with another coding rate, a little bit lower coding rate, then you get a special efficiency like this, right? I'm sorry, the higher code rate, like this. And eventually, the difference between all these things, all these different MCSs, MCS corresponds to modulation coding scheme, right? This is the terminology that the people use in industry. Okay, they do not call that as adaptive modulation; they call that as MCS. And using the same modulation, they change the code rate. They make it higher, higher, higher. Okay, and then once you higher your coding rate, you get more spectral efficiency. We talked about that, right? So what is the highest value of code rate? 1. Yeah. What means no coding. Because no redundancy, right? 1 means no redundancy. Your input is same as output. Typically, when you do the rate, the coding, right? What you do is that you have an input, some size over your input. Okay, input. And then you put some redundancy on it so that your output from the encoder should be larger because you added redundancy. But that's the coding rate basically means the rate between these two. Okay? So it cannot be 1, cannot be higher than 1. 1 is the maximum because 1 means that you have no redundancy, this one and this one is the same. Okay? Code rate 1/3. 1/3 means the output is 3 times larger than the input, right? That's 1/3. 1/3, right? So this is possibly something 1/3, like maybe 2/3, something like that. When you look at this table, right, and every system these days have this kind of table, MCS table. For example, you probably heard about WiMAX, right? LTE, and this one, 802.11n. This is wireless LAN. This LTE and WiMAX, those are cellular system, okay, cellular, mobile cellular system. This is a wireless LAN. As you see here, these days, every system use this modulation and coding, adaptive modulation and coding. They also change the modulation. They also change the coding rate. Okay? But each system has a little bit different approach. Here in the 802.11 case, wireless LAN case. As you see here, they shows you the modulations they use in the spec, BPSK, QPSK, 16 QAM, 64 QAM. They also clearly defined their own coding rates. It's pretty clear, like half, 3/4, and 5/6, right? These are actually the popular coding rates. So they actually put them together and make a combination. BPSK with half, QPSK with half, QPSK 3/4, things like that, right? So it's pretty clear from the modulation and coding rate perspective. Okay? When you put this together, then you can actually calculate what would be the spectral efficiency. This table does not show that, but you can calculate that. Okay? However, in LTE case, they approach a little bit different way. They are not trying to approach from the modulation and coding. Okay? They do not start from modulation and coding and put them together, try to calculate the spectral efficiency. They are not doing it. What they are doing instead is that they have a modulation and they start from spectral efficiency like this. And then from these two, they are trying to pull out what coding rate we have to use. Okay? It's a little bit different approach. But anyway, eventually it's the same thing. One code rate, one modulation eventually gives you one spectral efficiency, right? So which two you use, try to find out the other, the same thing basically, but they try to do it different way. That's why you don't see the code rate for each of them, right? You start the QPSK or any modulation with some spectral efficiency, then you calculate the code rate from these two. The code rate is not going to be now half or 3/4. It's going to be some fractional number, okay? Some weird number for code rate. But anyway, here as an example, you see that using the 3 different modulation and several different other code rate, therefore we have these many choices from 0 to 30, generally 32. These 3 are reserved for some other purposes, but anyway, this one is the table. And typically, the size of MCS table, like this, okay? The size typically is the power of 2, or power of 2, right? This is a 32. And sometimes, in fact, the 8 to the 11, wireless LAN case, the size of MCS table is 64. It's always like 2 to the power, because the reason is receiver, okay? All these things has to be measured in receiver, right? Why is that? Because which one you choose, whether I choose QPSK, whether I choose this code rate, all these things, which one to choose depends on the channel. So receiver only knows the channel, right? So receiver has to propose, okay, my channel condition is like this. So I like to, based on my channel condition, I propose to use MCS 8. Something like that, right? Okay? Or what the receiver does is that, okay, my channel condition is this. Okay? So therefore, I'm telling you that my channel quality information is 6. Okay? Something like that. So receiver will feed it back to the transmitter. So this is a case of a wireless LAN 802.11n. 11n is a extension of wireless LAN, and this one has a MIMO. So therefore, you see that the number of spatial streams, one water pipe, 2 pipe, 3, 4 different spatial channels, right? And they use modulation coding like this combination repeatedly. Therefore, we have 32 MCS right here. This example shows you that the case of OFDM. Okay, so earlier in the picture we talked about that you can use a different modulation based on the time varying channel, based on the time variation of the channel. Same thing can be done in the frequency domain. This is a frequency domain, and when the time domain changes, frequency domain the frequency response also changes. This one also changes. So this one is just one snapshot at one instant time, and depending on the subcarrier, you have a different channel quality. So this is a transfer function, right? Frequency response of the channel. Okay, some subcarriers, some of the frequency range, you have a high channel quality, so therefore you can have higher modulation. Some other subcarriers, the channel condition is low, so you have a low modulation. Okay, so depending on the channel condition of that particular subcarrier, you can allocate the different modulation. So this is very popular. In fact, every OFDM system, they have this adaptive modulation together in the OFDM. Okay, today we're going to review the multiple access techniques. Some of them may be popular, so you probably heard about some of these things already. So let's review some of the basics of multiple access. What is multiple access? Typically, multiple access basically means that there are many users who are trying to access at the same time. That's multiple access, simply speaking. Okay? So we have one receiver, we have a many transmitter, like that. Or maybe we have many receiver but one transmitter. Okay? Typically, right, what people say is that we have one transmitter. It doesn't have to be MIMO. Let's say that we have a base station here. Okay, we have a base station. And let's say we have many receivers, many users. Okay? This base station may transmit some information to everyone. Okay? This kind of condition is typically called as broadcast. Okay? So this is the condition of one to many. One to many, right? One to many is broadcast. Broadcast channel. We write it as BC. If you look at the information theory, some of the research papers and things like that, you probably heard about broadcast channel. Okay? It's BC, broadcast. So that's the condition of broadcast. That's called the downlink, right? In cellular system, they call that as a downlink. Because uplink, downlink, that always standpoint of base station. From the base station perspective, broadcast means downlink. Okay? So that's called the downlink. The other way, this is uplink. Okay? Everyone just transmit to the base station. So this is an uplink case. This kind of channel is called multiple access. Multiple access channel. They short it for MAC. Okay? So the information theory or some of the communications, right? They sometimes, often you hear BC and MAC. That basically means that the broadcast channel and multiple access channel, simply speaking, that's like uplink, downlink. Downlink, uplink. Okay? So when you look at the multiple access, always multiple access, that means this kind of scenario. Like there are a lot of users or a lot of nodes, okay, who wants to communicate with one entity, like a base station. This could be base station, this could be multiple, the access point. Think about wireless LAN, right? This may be access point, and you guys have all the Wi-Fi devices, right? Then it's again multiple access, right? There are multiple devices who wants to connect to the access point, so there will be a multiple access. Okay, that's multiple access. What's the problem about multiple access? The problem is that all these users try to talk to base station at the same time. So this base station receives all these things at the same time. A lot of people, right? A lot of people talk to me at the same time. Okay? Then when I hear everyone. So I understand nothing because that's all mixed together, right? That's the problem. Mainly, that's the problem of multiple access. So now what we are trying to talk about here is that given that condition, how this base station can distinguish each user's signal. That's all about it, right? Multiple access. Typically, we have a FDMA, frequency division, and time division, code division, right? Space division. There are also OFDMA. FDM has been very popular long ago because that's the easiest one, right? Time division, they appeared a little bit later, but still this is like a maybe 20 years ago approach, the technology. And later the TDMA, the CDMA appear. CDMA is popular for us, right? Everyone knows of CDMA, at least heard about the CDMA. There are also technology called the space division multiple access. We'll talk about briefly. This SDMA is about MIMO. Okay? We also have OFDMA, which is probably the most popular these days. Let's see one by one. Before talking about the actual multiple access, we want to talk about duplexing first. What is a duplexing? Duplexing is like how to deliver the channel, how to get the channel. Okay? So we are thinking about a duplex scheme, and there are, simply speaking, there are 3 different duplexing schemes. Simply, you probably heard about these things, right? Think about the road. I'm here, and I want to go to somewhere there. We have a road, okay? But this is just one lane. Either I just go, or someone can come, okay? It's not the two-way, right? It's not the, so this is just like a simplex, just one-way road. So this simplex is like one way. You can only go this way, okay? This way, no, okay? You only have to go this way. That's a simplex. And half duplex is that it's still one lane, but you can either go this way or this way, but not at the same time, okay? Not both ways at the same time. That's a half duplex. Duplex, this means that we have 2 lanes. So you can go and come at the same time. That's duplex, right? So we are talking about this one now. Also this one. That's a duplexing scheme. Okay? This simplex, of course, this is we are not talking about this one. We are talking about either this one or this one. Because in communications, we are always trying to transmit and also receive, right? So we are talking about these 2. Now then, there are 2 different ways. Simply the frequency division multiplexing. What that means is, here's a reverse channel, it's a forward channel, but this one actually is same as the downlink channel and uplink. Okay? Downlink and uplink. So some people call that as a downlink and uplink in the cellular system, right? But some other people call that as a downlink, same as a forward. Downlink from the cellular, that means forward channel. And reverse is the uplink. Again, from the cellular, the base station perspective, going out is going to be forward, coming back is reverse. Okay? So these 2 terminology, same as downlink and uplink. Okay? So you should not be surprised about this terminology, right? Reverse and forward. For downlink, uplink, they use a different frequency. That way, you can do the duplexing. In that case, transmitting and receiving, they use a different frequency. Definitely, it's a full duplex, right? You can transmit at the same time you receive. Full duplex. Because this is something like 2 different lanes. Okay? Now here's one question. Simple question. Maybe someone has some idea. Downlink, uplink, right? Downlink is what? Base station transmit, that's downlink. Users transmit, that's uplink. Let's say we want to separate downlink and uplink with the two different frequencies. Which one do you want to use with the low frequency? In this case, right, I use the uplink with the low frequency and downlink with high frequency. But you can change it, no problem, right? As long as you want to separate them, I'm good. So you can reverse it. Then why do you want to make uplink to have a low frequency, downlink with a higher frequency? Why not the other? Anyone has an idea? Make a little bit close. Yeah, a little bit. Yeah, that's a little bit close. But yeah. Yeah, that's right. Yeah, that's right. Did you hear what he said? We talked about wireless channel before, right? Wireless channel. Think about the propagation in wireless channel, like a free space path loss law, right? When you transmit some power, right, along the way that the power is attenuated. But that attenuation depends on the frequency. Okay, how much further you can go with how much further attenuation you get, that depends on the frequency, right? Let's say you have a very high frequency, right? In that case, by physics, okay, you have a more attenuation. When you have a low frequency, typically even with the same power, it propagates longer distance. Okay, that's physics. So therefore, in uplink, you want to have a low frequency so that uplink transmission you want to make a transmit a little bit longer with the same power. Why is that? Why is that? Why do you want to make uplink transmission to go further? Huh? This is uplink. Because this is downlink, right? Downlink is what base station transmits. Base station never worry about the power, never worry about the cost. Okay? They can have so much power. So if the base station's transmission does not go further, then I can increase the power. Okay? No problem. This is uplink, right? In uplink, users transmit. So let's reverse this so that the uplink transmit a little bit higher frequency. In that case, in order to receive the same power in the base station, okay, the users have to transmit more power. That's definitely you don't want to do, right? You want to make the users to transmit as low power as possible, okay, so that they can save the battery. They can make a longer battery life. Okay, so that's why they design it this way. Okay, this uplink, we want to make it propagate a little bit longer with the same power. Okay, some behind story. Anyway, in duplex, you have uplink and downlink to be separated by frequency, two different frequencies. Okay, so they can do a full duplexing. Now let's think about the time division duplexing. So TDD. In that case, we have only one frequency. Okay, but with this frequency in time domain, you basically change it from the uplink downlink like this. It's like a walkie-talkie, simply speaking, right? When you transmit, then the other guy has to listen, and when the other guy transmits, then I'm going to listen. Something like this. Okay? This one, you can say that looks like half duplex. Looks like, right? Because there's only one lane, and it's divided by time slot, and for each time slot, you transmit, receive, like this, right? Looks like it's like half duplex. But this rate of change, like this time slot, the size of time slot is so tiny, so that the people cannot distinguish. People cannot tell. Okay. So the people, if this time is significantly large, then people feel it, right? When I transmit, when I listen, then I cannot speak. People can find out, right? But this one is not significant. This is very, very tiny. so that they have to do a lot of fast switching. So the people do not realize. Okay? So that's the time division duplexing. Here it says the FDD, we typically call this FDD, TDD. FDD, you can expect high performance simply because we have two different lanes. Okay? This one has only one lane in frequency, so therefore this one you can expect a higher performance. But this one has one problem. Duplexer is needed. This one, you don't need a duplexer. Okay? Some of you who took my course in the previous semester probably talked about duplexer, right? So what is a duplexer? Remember that? Why do you need that? That's right, but these are separated anyway, so why do you need that?
Because there's some interference and you need to have a duplexer distance in between.
Okay, you mean the guard band, right? Yeah, partly, right? But why do you think there's an interference? Because we separate enough like this, then why do you think that there will be interference?
If you are transmitting and receiving at the same time, then
That's right, but yeah, let me add a little bit more explanation. What he's saying is right. But here's a condition. Yeah. This is from the user perspective. Okay? Let's think about from user. Reverse channel, this is a uplink, so this is what you transmit from the user, right? This is what you transmit. This is what you receive. Okay? Right? Let's say from user perspective, what will be the receive power? Typically, what is the power level when you receive? It's like a minus 80 dB, 80 dBm, things like that. It's very, very extremely low power. That's what you receive, always. Okay? Think about what is the typical operating range, SNR range. Actually, every cell phone has some engineering mode or something like that. Or debug mode, so that the developers can only go into. Okay, there's some mode like this. Okay, because the engineers, when they develop it, they have to go to the field and they actually have to measure it, measure the signal quality, measure the operation, so they have their own mode. Okay, for each device. There's some password, then you can type in, then they go into that mode. In that mode, you will see the SNR. Okay. You always measure the SNR. And typically, when you go to the field, what would be the SNR range of your cell phone? If you are in a good area, which have very strong signal, maybe you get SNR of maybe 70, minus 70, of course, minus 70 or 80 dB. SNR is dB, right? Not dBm, dB. If you are going to a little bit bad site, maybe your SNR goes down to minus 100, minus 105, something like that. But still your cell phone works. Okay? Still you can communicate. So now think about that your receive power. Typically the noise power is like minus 110 dBm or minus 120. Okay? So compared to that noise power and considering the SNR that I just talked about, your signal power you receive. Okay, your cell phone typically receives like minus 80 dBm, minus 90 dBm. Sometimes, if you are in a very, very good condition, minus 70 dBm and things like that. That's the receive power. Or sometimes minus 100 dBm. That's the power you receive. So now let's think about simply minus 100 dBm. Minus 90 dBm, let's say. This is your receive power. So how much power is this? This is dB, right? dB case. So what is the power, actual power? Let's say 0 dBm. What is the power, receive power? 1 milliwatt. Okay? dBm means it's milliwatt. Okay? 0 dBm is 1 milliwatt. Now then 10 dBm is 10 milliwatt. Minus 10 dBm means 10 to the minus 1 dBm, milliwatt, right? So this one is what? 10 to the minus 9 milliwatt. Extremely low power. That's what you receive. It's so low power. Okay, your cell phone basically captures this low power and it's operate. Okay, now let's think about that. Your transmit power. Okay, you transmit. Your cell phone can transmit sometimes like a 10 dBm. 10. Not minus 10, just 10. Maximum typically it's 24 dBm. Okay. This is extremely high power compared to this, right? It's like a 10 milliwatt, or it's like a more than 100 milliwatt. It's like it's like a 300 or 400 milliwatt. Why do you transmit these high power? Simply because your base station is very far away. Your base station is like several kilometers away, right? So you transmit this much power, this high power, so that it actually travels and propagates, and it delivers by the time your signal is delivered to the base station will receive something like this power, okay? Because of this propagation loss. So considering the propagation loss, you have to transmit this much power. That way, eventually, the power is tiny. That's what base station is receiving. But in the receive, it's the other way. Base station transmits this much power, and it delivers throughout the propagation channel. And when I receive it, I receive this so little power. Okay? So it's like if you think about the ratio, right? It's the 10 to the 10 kind of ratio, right? Given that, coming to here, and let's put that into this picture. This is what you transmit, this is what you receive. This one has a so low power. This one has like 10 to the 10 times power. Okay? That's the case. So therefore, simply, even though you separate them out by frequency, this one is so low, so high, not just 10 times, 10 to the 10 times, like a millions, like a trillions times larger than this one, so that this power will smearing into this. Okay? This power will, even with a very, very little interference, that will be a huge interference to them, because this is so low. Okay? That's why we need a filter. This is a filter. Okay? We need a filter to separate these two. Okay? Simply, we have to have a filter. That's the reason. Because of a very, very uneven amount of power you have to have a duplexer. And this duplexer is not a circuit. It's not like a resistor or capacitor. Actual device of duplexer is like a stone. It's stone, actually. If you look at actual duplexer, it's a stone. Because this one is RF device, right? This filter is RF. Just right after the antenna. Okay, as soon as you get the signal from antenna, you have a duplexer right there. Okay, in RF frequency, you cannot have like RC, passive filter. So you have some very special stone. But if you look at this stone inside, right, there are patterns, some very special patterns. And how to design the pattern into the stone, that decide your filter characteristics. Okay, so it's a very special one, and not many companies can make this. Okay, there are only a few companies in the world that can make this duplexer device. Some of the Japanese companies and some companies. Okay, very expensive one. Anyway, so this FDD device will have duplexer, but in TDD you don't need it because you have only one frequency, right? So that way, typically TDD system is cheaper because this one is kind of expensive. So CDMA, every CDMA phone is this case. CDMA is duplex, like the FDD. GSM, this one. Okay? So typically, right, from the hardware perspective, GSM phone should be cheaper. Okay? European, standard, right? Because of all these reasons. We talked about multiple access technologies like FDMA, TDMA, SDMA, and all these things. We're going to talk about each of them a little bit more, but we talked about multiple access technologies. We just talked about the duplexing technology. And these two, when you put these two, you can make a combinations. You use FDMA for multiple access, but you can use FDD for duplexing. Or FDMA, you can use TDD for duplexing. Okay? FDMA, FDD, FDMA, TDD, TDMA, FDD, TDMA, TDD. Any possible combination is good. Okay? Any combination is possible. For example, here, right? This is the case of FDMA, FDD. Why is that? Now, let's think about only one user, user 1. User 1 used these two, downlink, uplink, right? So therefore, it's FDD. And users are separated by frequency. So therefore, it's FDMA. Okay? So this picture shows you this case. Now let's think about this case. This is actually the case of CDMA. CDMA, typically they use a FDD. Okay? There is a CDMA slash TDD. Okay? There is some standard CDMA with TDD. That's not that popular, but that is only used in China. China, they use this standard, their own standard. All the other region where they use CDMA, they use this one. And this one is the case of CDMA with FDD. Each user uses FDD, but users are separated by CDMA. Okay? Now let's look at the FDMA, TDD, all the multiple access technology. As you know, in FDMA, users are separated by frequency. So typically, this is a narrowband system. Narrowband. Okay? Narrowband. For wideband systems, these days, we typically think about wideband system because we are thinking about high data rate system. But earlier, like 20 years ago, every system was a narrowband, like this one. Because at that time, like going 20 years ago, all the communication like this was based on the voice communication. Okay? That is what happened, right? Maybe 20 years ago. Everyone was using voice communication. So in order to deliver your voice, okay, voice channel, your bandwidth of your voice signal is like 4 kilohertz. Okay? Maximum 8 kilohertz. So that's a narrowband. Okay? If you deliver only the voice, that's going to be narrowband. So each user is narrowband. This example shows you the FDD as a duplexing scheme, and each users are separated by frequency, and each one is a narrowband. Okay? So that's the FDMA. And as an example, there was a standard called AMPS. This is the American Mobile something system. That was the analog system, analog cellular system, which used maybe 30, 40 years ago. No one used this one these days. Okay? This is analog system. No one is using analog cellular system these days. Everything is now digital cellular system. So this FDMA is kind of very old one, okay? But probably easy one. Later, okay, a little bit later, technology is a little bit advanced, and they think about the TDMA, time division multiple access. So here's the example. This is the case of TDMA slash FDD. You see that the uplink channel and downlink channel, they are separated by frequency. So therefore, this is FDD, duplexing. But it is also divided by time. User 1 use these two frequencies during this time. User 2 use these two frequencies, same frequencies with another time. Okay? So the users are separated by time. Therefore, this is called the TDMA. Example for this TDMA system is GSM. Okay, you guys know GSM, right? This is still popular, even with the 20-year-old technology, maybe 25-year-old. Still, it's very popular because it's very simple and devices are cheap. It's a pretty good system. So that's a GSM. That's a good example of this system. Okay. So users will share each frequency, each channel. You can actually, in actual system, they combine together FDMA and the TDMA. What that means is we have several different frequency channels. Let's say we have 3 different channels. Okay? We have 3 different channels available. And then for each channel, you make a TDMA. Okay? You have several different users for each channel. So in this case, user 1, 2, 3 use the channel 1, frequency channel 1. User 4, 5, 6 use channel 2. 7, 8, 9 use channel 3. Okay? So each channel is separate by time, so therefore it's a time division, multiple access. But the users are also separate by FDM, the frequency. Okay? So it's a combined. This is what is actually used in GSM, for example. We want to learn something about the CDMA because we know the CDMA, and this is actually pretty popular these days. Earlier in the FDMA, users are separate by frequency. In TDMA, separate by time. But in CDMA, there's no such separation. Everyone is using the same frequency, same time. Okay? Everyone uses the same thing. Okay? Then how do they communicate? Everyone uses the same. So here's the case. I'm here and I want to talk to 3 different guys. Okay? And these guys talk to me at the same time. Okay? Then how can I distinguish? That's the question. Okay? Earlier in FDMA, right? 3 guys use a different frequency, so I understand that. And in TDMA, these 3 guys are talk one after another. They use a different time, so I understand that. But in this case, they talk to me at the same time. But what is different here is that they use a different code. Each one is using a different code. What does that mean in here? In this illustration, in this case, I can illustrate as the 3 guys talk to me at the same time. Okay? But each of these guys use different language. That's code. One language, another language. Okay? Then I can understand, as a base station, I can understand the 3 different languages. In that case, at least if I listen all these 3 languages, even though they mix together, I can somehow distinguish because they use different languages. And suppose that each language has no correlation. Okay? There are some languages which have a very similar pronunciation and things like that. Okay? In that case, it's very hard to distinguish. But let's say, English, Korean, and things like that, this is very different language. So when I listen to these 2, I can somehow distinguish, right? That's a concept. Use the same code. Each user use a different code so that I receive 3 or more signals at the same time, but I can distinguish. So IS-95 is the first commercial standard using the CDMA technology. Okay? And they evolved into some other standard. Later, CDMA 2000 and wideband CDMA, WCDMA. Okay? And they have some generations using the CDMA. Now let's understand a little bit more about CDMA, how things work. Okay? So as an example, we think about 2 different users, user 1 and user 2. Okay? And user 1 has original information of 1 minus 1. Or suppose we use BPSK. 1 minus 1. That's the user 1's original information. User 2, this is user 2. User 2 has the information 1, 1. Okay? Again, BPSK. It doesn't have to be different. It could be same because each one has its own information to transmit. Now, when this user 1 transmits its own data, okay, you do not transmit as like this. You multiply your own code. This is the code for user 1. This is user 2's code. Okay? User 1's code looks like 1 minus 1, 1 minus 1. User 2 has the code 1, 1 minus 1 minus 1. Okay? And there is a reason why we pick the code like this. But anyway, let's assume that these are the codes. This is the code for user 1. This is the code for user 2. Now what you want to do is that you want to multiply this code into each of these bits of your information. Same way, you multiply your code into each piece of bit, okay? Before you transmit. Then you multiply this one in here, you multiply this one also in here, then you get this one, okay? Since this information is 1, you multiply this one, you exactly get the same thing. That's why you have same thing here. This is additional information, but starting from here, the second bit, 1 minus 1, 1 minus 1. That's this one, same way. And you multiply this one, this code into the second bit, but second bit is minus 1. So therefore, each of them is reversed. So therefore, you get minus 1, 1, minus 1, 1. I have additional 1 here, 1 bit here, 1 bit here, okay? Because I have a little bit here, a little bit here, okay? Anyway, think about the middle 8 bits. It's not a bit, in fact, because this is a bit. This is called a chip, okay? 4 chips, in this case, 4 chips per bit, okay? This is called a chip. So once you multiply this code into the bit, now these have chips. This is chip rate. We call that as a chip rate, okay? This is a bit rate. Originally, a bit rate, we multiply then chip rate. So this is what you get. Same way here, this is the code for user 2. You multiply this one in here and also here, but the original information is 1, 1, so you just simply get 2 times of this one and this one, okay? So that's what you have. And now, this is what you transmit, okay? That's what you can see in the time domain. Let's look at in the frequency domain. When you have this signal, original signal like this, you may have this signal in frequency domain. Your bandwidth is like a BS. It's a narrowband signal. This bandwidth depends on your symbol duration, right? If you have a narrowband, that means you have a low bit error rate, low rate. Now when you multiply this chip or code, right? Everything becomes now within chip rate. So therefore, it's you have it's a fast system. It's like a spreading into the frequency domain. Because simply you have this symbol duration, therefore you have this narrow band, but now you have this duration for each information, therefore now bandwidth is spreaded. That's why we call this a spreaded signal. Okay? So this is time domain, this is a frequency domain. Same thing happens for user 2. User 2 has this signal bandwidth originally, but when you multiply this one, now things becomes chip rate, therefore you have a spread it in frequency. Now the user 1 and user 2, they transmit at the same time. Okay? Since these two goes over the air, at the same time they will be added in the air. Okay? So from the frequency domain perspective, this one and this one will be added on top of the other. It's like a mixed, basically. So you have both of them at the same frequency region at the same time. And these two will be now added in time domain. So let's add these two. 1, 1, 2, like a minus 1, 1, 0, like this, right? This is like an extreme case, okay? Just to help you, understand. Just simple illustration. So let's add these two. Then this is what you get after your addition. This is eventually what is delivered to the base station, okay? We're talking about two users who wants to talk to base station, right? But over the air, this will be added together. That's what you receive in the base station. So now the base station receives this. Base station also knows this code. Base station knows that this is user 1's code, this is user 2's code. So using this receive signal, now you again multiply the same thing. Okay? Because in user 1, before you transmit, you multiply this code. So therefore, in order to recover, you multiply the same code. So let's multiply this code into the receive signal. Okay? So you multiply this one in here, here, and here. Same way, using this receive signal, you multiply user 2's code here and here. Then once you do that, you receive this signal. Okay? If you multiply user 1's code into here, you receive this one. When you multiply user 2's code here, then this is what you get. Okay? From this one, Now you have to go through the low pass filter. Once you go through the low pass filter, what is happening is that your signal will be smooth. Okay? This is called the smoothing filter, right? You make a low pass filter, now therefore your signal is going to be smooth like this. So therefore you get this one. After you do a low pass filter, this is the input to the filter, the output is going to be like this. When you put this one into the filter, again you do smoothing, then this is what you get. Okay? That should be same as the original information. Frequency domain perspective. Why do you need the low pass filter? Because this is what you get in the frequency domain. This is the received signal. When you multiply this, right? When you multiply the code in the receiver, this process is called the despreading. This process is called the spreading. Okay? When you multiply this, right, in frequency domain, you spread it. Therefore, we call this a spreading process. This is a despreading process. Once you do despreading process, it does not come back to exactly the original information. What you have is you have some other additional signals left and right. So therefore, in order to recover the very clean original spectrum, now you have to have a low pass filter like this. That way you remove all the other like a signal, right? Out of band spectrum. You want to clean the spectrum. Therefore you apply the low pass filter. Okay? So you want to get this original narrow band signal. So from time domain perspective, this is what you receive. So that's a basic concept. And now let's talk about why we want to have this code. What's so special for this code, right? In my previous illustration, I said that this one is same as a language. Okay? One language and another language. Now let's say I use a language like a French and maybe English. French and English may be similar, right? So that basically means that this code and this code is almost similar. Okay? In that case, you multiply these two code into similar, mixed together, it's very hard to distinguish. Okay? What is the best solution is that you want to make this code and this code to be orthogonal. Okay? We want to have orthogonality. What is the definition of orthogonality? Mathematically, the official definition is that you multiply your own, okay? This is, let's say this is C times C. You want to multiply your own, that becomes 1. You want to multiply another code, this times this one becomes 0. That's orthogonality, right? That's what we want. Because here, let's say this is C1, this C2, you multiply here. When you add it here, right? Let me simply write it here. It's very easy to understand here. Let's say our original information, let's say is A. Let's say A1 is your original information in user 1. A2 is the original information in user 2. In here, user 1 wants to multiply user 1's code. User 2 wants to multiply user 2's code into its own information, right? Now over the channel, this will be added. This is what you receive. That's this one, okay? You add it here over the channel. This is what you receive. So base station now receives this, okay? And receives this. And now you want to multiply user 1 code. Also, from the received signal, you want to multiply user 2's code. Okay? Then it's like you get this one. Here, this is what you receive, right? After you multiply the code, this is what you get. What we want eventually is that square, it's the code C1 times square, C1 times C1, that becomes 1. Same way, this becomes 1. This becomes 0. This becomes 0. That way, this whole thing becomes A1. This whole thing becomes A2. That's what we want, right? So in order to achieve that, we have to satisfy this property. C1 square becomes 1, or C2 square becomes 1, and C1, C2, 0. That's the original definition of orthogonality, right? So as long as your code, as long as the C1 and C2, these codes are orthogonal code, okay, then we achieve that. So therefore, you can perfectly recover your original information, A1 and A2. That's the whole fundamental of CDMA. Even with more users, still same thing, okay? As long as each user has the different code, but those codes are orthogonal, you will still have the same thing, okay? So now then, how do you design the orthogonal code? That's another thing. In this case, it's like this one and this one is orthogonal, right? How do you know that? You multiply this and sum. 1 becomes 1. Minus 1 becomes minus 1. So when you multiply these two, then you see that 1 minus 1 minus 1, 1. So therefore, you sum them, it becomes 0. Okay? So we see that this is orthogonal. There are many different ways of making orthogonal code, but the CDMA, the original CDMA system, they use a Walsh code. Okay? This code is called the Walsh code. And this Walsh code is how to separate the user. Okay? So the fundamental thing about CDMA and technology about CDMA is that they use orthogonal code called the Walsh code, and using those Walsh code, they separate the users. Okay? Not the frequency, not the time domain, but these codes, orthogonal codes.